Hi there. So in this video, we're just going to answer an electrochemistry tutorial sheet. Okay, so starting with the very first question, uh, we are told calculate the Gibbs free energy for the reaction. So we've got a reaction there, and then they want us to calculate the Gibbs free energy. Okay, so don't worry, with time, as you get more familiar with this topic, you'll be able to understand what the symbol stands for. That's Gibbs free energy. That part there indicates standard Gibbs free energy. And then there's also what we call standard cell potential, which will be like that. Okay, so one of the first things that you calculate under electrochemistry, you calculate what we call the standard cell potential. Okay, call it the E cell. So Gibbs free energy is dependent on the negative and Faraday's constant and then the standard cell potential, implying that before you can determine the Gibbs free energy, which determines whether a reaction is spontaneous, and of course by the reaction being spontaneous, we actually imply that it's favoring the product. Okay, so when it's negative, when the answer is negative for a standard when the for a Gibbs free energy, when it's negative, it's spontaneous. If it's positive, it's not. Well, it's the opposite for the E cell. If it's positive, then the reaction is spontaneous. So let's try to see what will happen here. So let's look at the reaction itself. Let me take you back to the reaction itself. The reaction was between copper 2 plus, I'm just copying that equation, and then plus the ion, giving us the copper solid plus the iron 2 ions. Okay, that's our reaction. Now let's try to observe the F reactions and see if they are actually written properly. So they are both written in a reduction form, so we have to see which one will become the anode there. So if we try to observe, just counter check against, copper 2 plus is on the left, so that's actually okay. Now if you check iron 2, they're on the opposite side, so we have to reverse that F reaction. So we'll start with that instead. So ion solid gives us the ion 2 plus ions aqueous plus the 2 electrons. Okay, so the moment you just do that, this value changes the sign when you reverse. So since it was negative there, it's going to become positive 0.44 after reversing. There are also cases where you find that the number of electrons are not balanced. In that case, you are required to balance up, just the way we used to balance a simultaneous equation. So you multiply this one by 2 throughout, but then that value is not affected by the introduction of multiplication. So at this point, things have become easy now. When you know which one is oxidation and which one is the reduction reaction. So this one is the cathode, and then this other one is on the anode where oxidation occurs in a galvanic cell. So therefore, when it comes to the calculation of the E cell, when you've reversed and you've changed the signs, just add the values. So the values therefore are going to be 0.34 volts on top plus 0.44 volts on the bottom. So that gives you a 0.78 volts. Other people would maintain everything as it is and just identify the anode and the cathode without changing the sign, and then they just say we're going to subtract the cathode by the anode. So 0.34 minus negative 0.44, which of course will just end up to 0.78. Okay, so calculating our Gibbs free energy therefore becomes substitute N represents the number of electrons, so you've got a minus 2 multiplied by the Faraday's constant, which will be given in your exams, and 6485, and 0.78, which is our standard cell potential. And so all you have to do is just grab the calculator there and punch the values. So the units for the Faraday's constant, coulombs per mole. Okay, so what will happen here is we're going to have a value of negative 150,729 joules per mole. Okay, which if you want you can divide by 1,000, so it just becomes negative 150.7 okay, kilojoules per mole. So these are the units for the standard free energy. Take note of it. So it's energy, so joules makes sense. Of course, the mole coming from the equation itself. So this is our answer. Now, is it negative or positive? It's negative. So would you say it's spontaneous or not? So the reaction was spontaneous, implying it was favoring the forward reaction or the product. Alright, so let's answer question 2. Question 2, we are told for the oxidation reduction reaction. That's the reaction itself. The appropriate F reactions are given, 1 and 2. Then we are told to balance a redox reaction. Of course, we need to calculate the standard cell potential and the equilibrium constant K at standard temperature 25 degrees Celsius. So, this value given in the question, in the worksheet, is unreasonable. So, the actual value there for the reduction potential for chromium actually is something like negative 0. Some show negative 0.40, some show negative 0.40, at least something like that. Okay, that's the reduction potential. So we use the accurate one, the actual one, at least something closer to the actual one, and overlook the one that was given. So when it comes to balancing, you need to make a decision. Okay, whenever you're dealing with a galvanic cell, you need to ensure that the spontaneous reaction is possible, and you have to be careful now you choose the anode and the cathode. So all these in their original state are given as reduction reactions. So that's why the electrons are appearing on the left side. Both have reactions. It's now up to you to choose which one to reverse. The simple secret in reversing is just reverse the one with the smallest value, and the moment you reverse it, the sign has to change. Okay, so in this case, which one has got the smallest value between this one and that one? So the one with a smaller value is the chromium, and so we can reverse it. If we do reverse it, we're going to start with that part. So chromium 2 plus gives us chromium 3 plus an electron. After reversing, the sign of reduction potential changes. It becomes 0.50 volts. Okay, then the other reaction, the other half reaction is S4O6 2 minus. We'll maintain it as it is given, and then that is the product. Okay, so we haven't tampered with this the half reaction, so maintain the reduction potential to be 0.17 volts. I think that's key to recognizing. And then looking at the number of electrons in this reaction, we've got 2 electrons, so we need to balance up even in the other one as well. So we multiply the entire equation just like we do simultaneous equations, so that the number of electrons can be balanced, and we can be able to now cancel them out, since one reaction will be releasing them, the other one will be receiving them. So the balanced redox reaction, therefore, have 2 chromium 2 plus S4O6 2 minus, giving us that 2 chromium 3 plus 2 S2O3 2 minus, right? Okay, so that's a balanced equation. You'd want to show the states, which are probably all aqueous states, right? Okay, so this is the balanced equation. Okay, unlike that one that we had on top there. So after you've balanced, now they also want you to determine the standard cell potential, which after you've reversed, just add whatever you have there. So our standard cell potential becomes 0.50 volts plus 0.17 volts, which would give us 0.67 volts as a standard cell potential. Okay, so that's it for the first two part of the questions. So we've determined the standard cell potential. Now they want us to determine also the K value. Okay, so how would we determine the K value? So the K value comes from the relationship that exists between the Gibbs free energy and so the Gibbs free energy and the constant K. How are they related? That's where the whole concept comes from. So that would be RT and then natural log of K, right? So that is a formula. Now this is what we call non-standard Gibbs free energy. This is standard Gibbs free energy, and when this is 0, this one becomes the subject of the formula. It becomes like this. So it will go with a negative there, so that you've got RT, natural log of K on the right. And if you divide both sides by the negative, you will now actually see that this will be negative RT, natural log of K. So this is a formula that we use when we are trying to determine the K value, because we can make K the subject. The standard Gibbs free energy, we understand it's minus NF E, coming from the previous question on Gibbs free energy, right? Where N is the number of electrons that were being transferred. And if you paid attention afterward balance, it was actually N is equal to 2. Faraday's constant is a non-constant value, okay, which will of course be given in your assessments, approximately 96,485, right? So then minus RT, natural log of K. You can actually notice a few things. The negatives can divide, so that you just have positives. Then divide both sides by RT. Okay, so what will remain ultimately is the fact that the natural log of K is equal to NFE over RT. And so at this point, if you want, you can write this in the simplified form, but I don't want to complicate things for you, so we can just go on and substitute. We understand from logs this is base E, so K becomes E, and then this becomes its power. Okay, just substitute directly. The number of electrons, that's 2. Faraday's constant, 96,485. The standard cell potential is 0.67 over RT. Now gas rate constant, the one that we use here is the 8.314 multiplied by the temperature in Kelvin. So 25, you want to convert that to kelvins, that will give you 298 kelvins. Okay, so that is your power. So grab your calculator there, 2 multiplied by that, and yeah, divided by 8.314 multiplied by 298, then raise that to, and raise e to that power. So e raised to that power. So the answer I'm getting as the final value of K is 2.77 times 10 to the power 22. That's the value of a constant K. In summary, the formula that you need to know is just that the Gibbs free energy, the standard Gibbs free energy, is equal to the negative RT natural log of K. That's all. We're on question 3 now. Question 3 says, use half reactions to write a balanced redox reaction equation for the oxidation of zinc metal by permanganate ions in acidic solutions. So these kind of questions, you'll be given the half reactions or the table of the standard reduction potentials. So what is involved in this case is zinc metal. So zinc metal, zinc solid metal, which of course in its original form would be something like zinc 2 plus 2 electrons is equal to zinc solid. Then manganese, permanganate ions. Okay, this is its equation. Okay, you don't have to memorize all this, it has to be given to you. Okay, so don't feel compelled to memorize it. When they need you to use it, it will be given to you. Okay, but it's not very complicated to take note of. Okay, so this is the way the equations appear in their original form. Now we are told oxidation of zinc metal. So this metal is being oxidized. So oxidation, I've already been telling you, oil and rig. Oxidation is loss, reduction is gain. That's what these stand for. Okay, oil and rig, I hope you remember that. So the fact that zinc was being oxidized, the electrons were being lost. So loss of electrons appears on the product side. So we have to reverse it. Zinc solid, and then zinc 2 ions, an indication that has been oxidized due to an increase in the oxidation number. Okay, 2 electrons. Now at this point we can't just balance directly because the number of electrons are not able to cancel out. We've got 2 in one, the other one we've got 5. So how do we strike a balance? How would you balance? What do we multiply with? Okay, pause the video and try to think of that. So 5 and 2. So we are just supposed to multiply this one by 5, that one by 2. Okay, so I'll just do that directly without rewriting the equations. So this will become 2, this will become 16, this will become 10 when you double. So 2, that will become 8. For the bottom, so this entire equation on top we've multiplied by 2. The one on the bottom we multiply by 5, so that will be 5. That will become 10 when you multiply by 5. So when we balance them, we maintain whatever is on the left. So you have 2 manganese, 2 permanganate ions, plus 5 zinc solid, plus 16 plus ions, giving us 2 manganate ions plus 8 water molecules plus 5 zinc ions. So we've balanced, and if you try to actually pay attention or count, you'll be able to see that we've balanced. The number of oxygen here is 2 times 4 gives us 8, which is the same there. We've got 5 zinc, 16 hydrogen. Okay, so basically that's how you handle question 3. Oh well, just had to jump in case you're enjoying this video, which I guess you are. Wanted to let you know on our site you're able to learn electrochemistry and some other chemistry topics. In fact, all the chemistry topics from scratch at your convenient time. So if you've forgotten some concepts, you want access to tutorial sheet solutions and past papers, head over to our site. The link is in the description below. And we've actually answered up to 16 questions in this tutorial sheet. See you on the other side. Question 4. Question 4, we are told using the following standard potentials, calculate the standard potential of copper zinc cell. We've done this question numerous times now. You should now have the courage to be able to answer it. Okay, so look at the values. Which one should we reverse? Is it the zinc one or the copper one? Okay, so based on the value, which one do you think is lower between the two? So the lower value there is the one for zinc. So if we reverse it, we'll start with zinc solid and giving us zinc 2 plus ions plus 2 electrons. So this is the guy that will become the anode. Okay, the value changes to a positive 0.67. The other copper one will be maintained. Okay, with its value remaining positive 0.34 volts. Okay, so when it comes to the calculation of a standard cell potential, it just becomes the addition of the two values. This is question 4, right? So 0.76 volts plus 0.34 volts. So that would be 1.10 volts. Okay. So that's our standard cell potential for question 4A. As simple as that appears. Okay. So question 4B is the question that I want you now to have a look at. Is copper metal expected to react with dilute hydrochloric acid? Is copper metal expected to react? So whenever you see HCl, HCl is a strong acid. Expect dissociation of the hydrogen ions from it and the chloride ions, complete dissociation. Now, is copper metal expected to react with the HCl? Is the question. So the equations that would be involved is a reaction between copper and hydrogen in the acid. Okay, so the equation for hydrogen is that, which is the only neutral equation with a reduction potential of 0.0 volts. So how do you tell that a metal is able to react with hydrochloric acid? How do you tell? So hydrochloric acid is only able to react with the ones that have got a lower value. Okay, a lower value than 0.0. Okay, in other terms, only the metals that are more reactive than hydrogen are able to actually to react with hydrochloric acid. Okay, so copper is less reactive and it won't be able to react. Okay, so the ones that have got when you compare, for example, the ones that are on top there, you can see that zinc has got a negative value, implying that zinc is actually more reactive than copper. So the one that is more reactive is the one that actually goes on the anode, or the one that gets oxidized. Okay, so and we saw that you go by the smaller value, right? So the only values of the only metals that can react with hydrogen are the ones that have got lower values or negative values. They are the ones that are more reactive. The ones with the positive values cannot react. So the simple answer there is it cannot. The reason is simple. the hydrogen ion is a weaker oxidizing agent compared to copper, so it cannot oxidize the copper metal. Okay. Alright, so answer question 5. Here we are told calculate the cell potential measured at almost zero current produced by a fuel cell in which the reaction is 2 that plus oxygen giving us water, with hydrogen and oxygen each at 25 degrees Celsius and a pressure of 100 kilopascals. So whenever you see 25 degrees Celsius, just know these are standard conditions. So our calculations are going to be simple and straightforward. Just calculate the standard cell potential based on the given data. So calculate the cell potential. Okay, so that's the standard cell potential because we're 25 degrees Celsius. Okay, now if you try to observe what we've been given, this is 0.0 volts for an information whenever you see hydrogen. Okay, so to calculate the standard cell potential, we just need to add the values, and you only add the values if you've reversed what you need to reverse. And I said for you to reverse the smaller one. Which one is the smaller value here between 0 and 1.23? So it's 0, right? So even if we reverse, nothing will happen. So the standard cell potential will just be 1.23 volts plus 0.0 volts, which will just be 1.23 volts for the first one. Okay, standard conditions. Then for the other one, we are told what potential difference would be produced in a fuel cell operating with oxygen and hydrogen with both gases at 5 bar. So if you are new to a fuel cell, actually you would want to watch my video on that. So the link in the description below to our platform where you're able to learn electrochemistry from scratch. You'll be able to understand the fuel cell, galvanic cell, the Nernst equation, and everything else. Okay, so what potential difference would be produced in a fuel cell operating with oxygen given those new pressures right there? Okay, so the conditions have changed, and this is not going to be standard. So this implies you now need to work with the Nernst equation, which relates the standard and the non-standard cell potentials. Okay, and of course at 25 degrees it's 0.0592 over your n. Okay, and then log of q. So our q, of course, is the same as the calculations of k from equilibrium. Now this is at any point. So in this case specifically we're dealing with pressures. So if we look at if we can come up with a balanced equation for our reaction, it's that, right? That's a balanced equation. We have 2 hydrogen reacting with oxygen to give us water. Okay, so the calculation of K and Q is products of the reactants, right? So products of the reactants. Okay, don't forget your equilibrium. So for our products, this is in liquid, the others are gases, the reactants. So products, whenever you've got liquids and what solids, you put a 1. Okay, so 1 to the power 2. Then for the reactants, you've got hydrogen, which was at a pressure of 5 bar, so it will be 5 squared due to a stoichiometric coefficient. Oxygen 5 as well to the power 1 in respect to its value. 5 squared is 25 times 5, that's 125, so 1 over 125. So the value of Q essentially is what? So our value of Q is 1 over 125, which is actually going to be 0.008. Okay, so that's our value of Q. And we can make some changes now. So our value of Q has been determined. The number of electrons, if you balance by multiplying by 2 this other one, you find that you are going to remain with 4 electrons. So N it becomes 4. The standard cell potential was determined to be 1.23. Okay, so we can substitute. We'll have 1.23 minus 0.0592 over 4 electrons log of 0.008. Okay, this is why it's important to understand different parts of chemistry. Pay attention to every topic. So if you are stranded, you've forgotten how to go about your chemical equilibrium, want to do a quick recap, everything is available on our platform. All the topics are already there and you can easily do that. So our cell potential will be 1.23 and log of that is just going to be negative 210 multiplied by this, which essentially gives us 0.031, which if you add will be 1.261 approximately. Okay, volts. So what difference are you able to notice here? What are you able to notice? So when we increase the pressure of the gases to 5 bar, we've observed that we've gotten to a potential difference of 1.261 from 1.23, which is an increase. Okay, so this actually explains why in the industrial fuel cells they often operate at higher pressures so that they can achieve a slight higher voltage and efficiency. Okay, so increasing the pressure of the gases used in a fuel cell will lead to a slight higher value of the voltage. Okay, question 6. A common analytical oxidizing agent is an acidic solution of dichromate ions, for which that is a solution used for a redox titration of ion 2 to ion 3. Could there be a side reaction when chlorine are present? Okay, so that's the question at hand. Pause the video, please feel very free to pause the video and try it out. So let's try the equations first of all. We see what's happening. So a common analytical, you want to read the question again if you haven't understood. So the dichromate ions, the equation, the half cell or the half reaction is going to be that. So again, I'll mention these are always given to you in assessments. Okay, so 6 electrons. So in this case you don't even have to trouble yourself because you can actually look at the values that are given there. Okay, so 6 electrons and then gives us 2 chromium ions plus 7 water molecules. I'm interested in the value 1.38 volts given to us. Then for the ion 3 to ion 2, this is 0.77 volts. So I'll read the question again. A common analytical oxidizing agent is an acidic solution of dichromate ions. Okay, for which its reduction potential is 1.38 volts. Is the solution useful for redox titration of ion 2 to ion 3 ions? Could there be a side reaction when the chloride ions are present? So this oxidizing agent, dichromate ions, is it sufficient? Is it able to reduce this guy to that? So to make that decision, I can even just remove that. Just observe the values. Okay, that's 1.38. This is 0.77. So the one that is reversed is the one that's going to be oxidized. Now, is it possible that this can be reversed? So I said reversal happens to the smaller one, right? So which one is the smaller value between the two? Imagine we're trying to form a galvanic cell. Which one should we reverse between the two? So we reverse the smaller one, which is 0.77 volts, right? So which would now become negative 0.77 volts after reversal, implying that we're actually able to do that. So what happens if we reverse it? The moment we reverse it, it actually becomes the opposite, right? Ion 2 to ion 3 ions, which implies it's now getting what? Oxidized. So it's actually possible for us to oxidize it using the dichromate ions. Okay, and this is the reaction that will happen on the anode. So by observing the reduction potentials, you're able to see the one with a smaller value can be oxidized. So that's what you look at. So could there be a side reaction when chloride ions are present in that reaction? So what do you think there? If I was to give you the equation for the chloride ions, so which is also 1.36 volts. So you notice that the reduction potential for chloride is very close to the one for the dichromate ions. So apparently the dichromate could actually also oxidize the chloride ions because their value is slightly lower. Okay, so that would be the effect there. Okay, so this side reaction would actually cause interference, and it would lead to production of the chloride gas instead of only oxidizing the ion 2 ions. Okay, so I hope that makes sense. Yeah, that's it to question 6. And if you want to access all the solutions to the questions, you want to register on our platform using the link in the description below. I think the questions all in total are somewhere up to 19. So the questions are up to 16 plus. So you would want to watch that video and learn everything that you need to about electrochemistry. Thank you for taking time watching this video, and see you in the next one. I also need to mention that you can actually have access to the PDF of all the questions answered in this video using the link in the description below. Yeah. Oh well, just had to jump in case you're enjoying this video, which I guess you are. Wanted to let you know on our site you're able to learn electrochemistry and some other chemistry topics. In fact, all the chemistry topics from scratch at your convenient time. So if you've forgotten some concepts, you want access to tutorial sheet solutions and past papers, head over to our site. The link is in the description below. And we've actually answered up to 16 questions in this tutorial sheet. See you on the other side.